それではそろそろ始めたいと思います。So I think we will start now the next session. So the next speaker is David Przybilla, and he will be talking on the topic of reproducible data science using Terraform.
Yes. Hello, everybody. Sorry for not speaking Japanese. First of all, I work for this company called HD, which my coworker just gave a presentation as well. I moved to Tokyo roughly 1.5 years ago, and I'm gonna tell you a story about data science. And sorry, because my talk is the less Pythonic of all, probably it includes no Python, but let me explain the problem and the reason why I think this might be interesting for you. So the reason is many Pythonistas are into data science. And this is a tool I wish I had when I was doing data science. So this tool is about how could have been made me much faster at work and how could I had empowered my team. So this is my story. So I was doing data science, more or less data engineering between 2012 and 2016. I was essentially delivering data science models to production. And you think I will spend most of my time doing statistics, but actually I spend most of my time in data engineering. So this is one of the problems that I was solving back at work. It was called topic extraction. I'm not going to go deep into that because it's not the focus of my talk. But essentially you have a news article or an article, a blog post, whatever piece of text, and you want to identify the topics in it. So given this example, you might say that Barack Obama is one of the topics and is 80% relevant, or that Apple Inc. is one of the topics there and is 19% relevant. And you can go on and on until, for example, you find sushi and it's 1% relevant. So to achieve or to solve this problem, you have to gather some data, transform it, building a model, and evaluate it. The truth is we spend most of the time transforming the data and running a scripts to transform the data. And there was a cycle where we have to rebuild the model to update it to be able to extract new topics and so on. So we had a large corpus of, let's say, around 300 gigs, which we had to clean the text, count words, and create something called word embeddings, which is not important now, it's just a bunch of numbers, and build a topic model, which is essentially just a bunch of numbers for the sake of this talk. So that requires a lot of infrastructure. So just batch processing, just counting words require a lot of infrastructure. We had a Spark cluster and everything that comes behind that. And it started as a collection of bash scripts. Remember, this is 2012. So we had a bash script that was bootstrap.sh, and that one would create an infrastructure. We have another one called spark.sh, and that would start or stop at Spark cluster. And we had another one which was called extract text, and that one would start the application on a Spark that actually processes the text. And we got another one which actually started the application that counts the statistics. So if one of these scripts failed midway, we have to manually destroy resources. We have to rerun, usually from the beginning. And all of that, believe me, took a long time because we had to make sure which data was running with and so on and so forth. So our pipeline became more and more complex with more data and more sources of data and more complicated models. So many of these issues are addressed by some tooling now in 2018. But let's hold down for that thing for a second, and also think that we had to run experiments to answer business questions. So some of them included what is the favorite football team of a user? So it is okay to experiment with a small data set in your computer. It's really easy. You just set RStudio or have an IPython console with you. But when data grows, it gets harder to run and store outputs of whatever model you're generating. Because this usually meant more infrastructure. So whenever I face the infrastructure part, I have to talk to someone else or spend a long time figuring out. That slowed me down a lot. Not the statistics, which is what was the part that I was interested about back then. But I spent most of my time getting the data I needed in the infrastructure I needed. So experiments became harder to run. There were a lot of custom scripts. I couldn't work, like coworkers' experiments, they were completely unrunnable for me. Like it would just take me a whole day to figure out how to put all of that together. So compile this for this library X with GPU support, run this batch to create the cluster to run X application. That was a lot of complicated things to do. So scaling up an experiment required a lot of clicks, UI, failed middle steps. And back in 2016, people started talking about reproducible data science because people are angry. They were unable to verify results. You will see a paper or you will see like a GitHub repo saying that they achieved some very amazing results, but you won't be able to verify them. So what is reproducible data science? Well, it's essentially that someone else should be able to recreate your model's results. You should tell them which version of the data, which version of the code, and it should be rerunnable. And you should get the same results. You should be able to generate them. So as crazy as this sounds, that was not a thing in data science until very recently. So nowadays people are Dockerizing their setups as much as possible. I think we are done with this as in 2018. You see a lot of like Python, like Dockerized, NumPy, and Conda things. But this field is still far from other lands of software engineering. There is so much that data science community can learn from, well, DevOps, which is what I work on right now. And I'm talking about retraining models, redeploying them, and making sure they are consistent. One of those steps is to handle infrastructure. And this is where this talk sits. So I'm here to tell you, if you're a data scientist, learning Terraform can give you a superpower. If you are a DevOps, you can empower your team through Terraform. What were my problems at that time? As more data came, I had to expand my experiment from my laptop to big machines. On larger storage, more CPUs, larger clusters, larger outputs. So I usually wanted to run an experiment for a day, and at the end of the day, destroy all of that infrastructure. I just wanted to get the numbers out. And I usually had to speak to a lot of people to get this done. This usually was a bit blocker and was what makes me slow. So it took me a long time to figure out setups. And Terraform is a tool to address that problem. You don't need to know many details, and that's why it's useful. Just some basics can give you superpowers. So Terraform introduces this thing, which is very cool in 2018, called infrastructure as code. Essentially, you describe your infrastructure in a file. You say, I want 3 servers, I want one database, and so on and so forth. And they call it HSL language. You send that, you pass that HSL script that you write to a tool called Terraform, and that's going to create it in whatever cloud provider you are using or you like. So to provision infrastructure, you just use HSL to describe how it looks like. So you can do that for databases, virtual instances, and load balancers. So in HSL files, you define what you want. So, and Terraform will know how to create, how to update, and how to destroy. So how does a HSL file looks like? Well, this is kind of the hello world if you looked it up on Google. This code defines a virtual instance on AWS. It's just this bit of code where this is a keyword called resource. It's essentially just saying, I want to create like a piece of infrastructure. This tells AWS instance tells like what kind of instance you want to create. In this case, well, an AWS instance, it could be anything else. And this is just an internal name you give, like a variable name to use internally in your scripts. And all of these things here are settings you can pass to that instance, like the size, for example, or tags or other settings. And then Terraform comes with this Terraform command. So if we save the example that I show you in sample.tf and then run Terraform plan, Terraform will talk to, in this case, to AWS APIs, figure out what actions are needed to achieve the desired state, which in my example is to create an instance, and show the needed actions. So be aware that no infrastructure will be created at this step. It just tells you the actions that will be required to be done. So it looks a little bit like this if I run it in my terminal. It will tell me I'm going to create an instance with all of these settings. Most of them are computed, since I didn't give all the possible set of settings I could have given to it. And then you do Terraform apply, which will talk to the AWS APIs, figure out what actions needs to do to achieve the state, and simply apply those actions, resulting in an instance being created. So Terraforms know how to create, destroy, and update. One thing is that HCL is declarative, so you don't tell how to build the stuff, how to build the instance. You just tell the state that you want. So if you run again Terraform plan, it's gonna tell you that nothing needs to be done because the current state has already been achieved. So actually, learning Terraform is only learning essentially these 3 commands, 90% of it: Terraform plan, apply, and destroy. Destroy, just as the name says, destroy everything you created. So this avoids telling people to click in a web UI and avoid bash scripts, which I really hate. So after finishing running your experiment, destroy all your infrastructure with a single command. I think that's really powerful. I know I'm not gonna waste money. I wish I had that tool back in 2014. But now you should be saying, okay, I'm a data scientist. I don't want to know all of these details of these cloud providers. And I agree with you, you shouldn't be worrying about that. But hold on for a minute before you leave the room. The real power of Terraform is in its modules. So Terraform module is an aggregation of infrastructure. You don't need to know how things are connected inside. You just import it and use it. So an example of a module could be a Spark module that creates, a Spark cluster, but a GPU Jupyter instance module that creates an instance with a GPU that has Jupyter inside. Or a stream processing module that uses whatever you want to do a stream processing. Or a module that has a Luigi cluster. And if you look at the steps, for example, to create a Spark cluster, you have to read the docs, figure out how to install it, create a VPC, and do a bunch of things. But if you use Terraform, it could simply be done with Terraform plan and Terraform apply. So because a module is like a function, and in the sense that a module only does one single thing. A module has parameters and outputs, but the inside is invisible to the importer. Like the Spark module, you wouldn't care how things are done inside. You would just say how many instances for that Spark you want. So the module abstracts complexity. So you don't need to know how things are connected inside. You don't need to see all the pieces. And a module is composable. You can aggregate modules to create bigger ones. The output of a module can be the input of another one. That's what I think is really powerful. So how does a module actually look like? Well, a module is just a folder with Terraform code. You want to make our sample a module? Well, it's already a module. So if I save that file in, let's say, into that path, then importing it and using it as a module would simply be requiring this piece of code below. The module keyword, which just tells whatever it's gonna be, here is gonna be a module that I will be importing. A name for this component, you can name it whatever you want. And a folder where the Terraform code of the module lives. And then that's it. If I try to run Terraform with this import module, it will try to create an instance in this case. So this is all the code that is required. So if I run Terraform plan apply, it will create what is defined in that module. And another cool thing is that modules can take parameters. So if I put variable followed by variable name, so variable is a keyword and variable name is whatever you want, then that module would take a parameter, just like a Python function. So if I add that to my Terraform code, and let's say I just added something that uses that name to create a tag for that instance, then when I import my module, I can just add that as a parameter and name my instance David Experiment, for example. So another cool thing is that you can import a module from GitHub. So you can take the module syntax, and if instead of a path to a folder, you give it a path to a GitHub repo, you can just import someone else's module, and you can log it to a commit hash or a GitHub tag. So this is really cool because there is a bunch of modules out there that do all kind of things. And there is also something called the module registry, which is essentially a place where Terraform team and other companies have already created a lot of like modules that are ready and battle tested to use. So how these change things? So a data science can have a minimal understanding of Terraform and still use modules provided by the ops team or the community. So running an experiment, well, just add Terraform as one of your steps. Terraform apply would be one of those steps, and then you don't have to think about bash scripts that are broken all the time. And data science team can reuse patterns of infrastructure to run experiments. That's all the magic I wanted to share with you today. And actually, there is a very interesting person I've been talking to about this topic, and he made a blog post called DevOps for Data Science. And if you are interested in this topic, I recommend to read that because he wrote his master thesis on this topic. And it's not exactly on infrastructure, but it's on the whole process of having a data, let's say a classifier model, and redeploying it constantly and making sure it changes as the business cases are changes as well. So give it a try. I gave him a poke before making this talk, since I wanted to get some of his input. And I also ran into this book very recently, which if you are into this, you should definitely read it. And that is Machine Learning Logistics, Model Management in the Real World. So most of the books assume that you build a model on some data, deploy it, and then it's over. But actually that model would change. And I had like awful experiences deploying classifiers that will get outdated in no time, because like literature back then did not address some of the issues. So this book is amazing if you are into like what is the pipeline that you should do when you, for example, deploy a data science model like a classifier. It's like all the DevOps around it. And obviously if you are into this, these are obvious tools that I did not mention, but you should always take into account. One is Spotify Luigi, which I'm not sure how many people are familiar with that here, but it's a lovely tool if you are rebuilding models and you want to make sure they are consistent. And the other one is Pachyderm, which is quite new, and it addresses a lot of the problems that I mentioned on this talk. So please give it a look. Thank you for everything. That's all what I wanted to say today.
Thank you very much. So I'd like to open the floor for questions.
Can I speak?
Yeah.
Sorry. Thanks. So I've run into the Terraform name, but I haven't used it yet because there's so many tools to learn. And but you mentioned data versioning, like versioning the data set. So from your examples, it looked more like server procurement. But does Terraform also have a way to version data and sort of that aspect of it? Because that's very big for reproducibility.
Oh, yes, you are correct. And no, this doesn't address, I was just mentioning some of the problems that my team had. I think that the AAT, that project, is probably one of the best tools you can use to version data. Back when I was using it, it was very primitive. But nowadays...
Which tool? Sorry?
Oh, DAT. It's just look it up. Sorry.
Yeah.
So that.
Okay.
Yeah. If you look it up, so it's like a GitHub but for data. Kind of. It's like you can commit a change to a data. So you can say this is a data set, and I want to commit a change to it. It doesn't store data. Well, it kind of stores data for you, but it sort of tracks the versions of the data.
And then it gives some kind of UI or something, so you can provision that in your, or I don't know, like what a Docker container, like pull that version of it. It
could also do that. Like it gives you back a hash out of it, and it's like a P2P, peer-to-peer tool too. So if you have it like locally, we'll just share all of your data. Looked it up because that was what worked for me back then. But for that data versioning, like you can also use Luigi. I'm not sure if you are familiar with it.
No, I have no.
So Luigi, you define like a graph and of actions, and then if at some point the graph fails at applying one of the actions, it will just start from where it stopped. But then like it can help you with that versioning, because to start a task you have to define a version of everything. So you just cannot say like run this function, but you have to say run this function with this data, and essentially that data would be versioned, kind of. So it also helps a lot.
Okay.
If that makes any sense.
Yeah, it does. It sounds really useful.
Yeah.
And then, if it's okay, I have one more question.
Oh, yeah.
Okay. So, Terraform, how does it play in with orchestration and scheduling workloads across nodes and stuff like that? You know, because I use Kubernetes, obviously, because it's popular and hip.
So
But you still have to set up the cluster and like provision it, which Terraform does for you, I guess.
So in this case, let's say Terraform will make sure to spawn all of the infrastructure you needed there. I'm not that familiar with Kubernetes.
Or like Docker Swarm or some kind of like another.
Yeah, I know what Kubernetes does, but I think they sit very differently. Like, this is pure infrastructure. I wouldn't be surprised if someone does something in the future. But for example, if you use the services from the cloud, you can define like your auto-scaling there. So in that sense, that's where you define the auto-scaling. So those will be where those settings would be spawned from.
Okay, but yeah. Okay, thank you.
Yeah.
In the center, just take
Hello, two questions on Terraform. Well, I'm hoping to pick it up soon. But one is, how about handling credentials? So let's say you have a cloud. What if I have a bunch of different credentials for a bunch of different accounts? Is that maybe easily possible? Because I've been burned by some tools that just assumed I only have one account. And another thing is handling errors in case something in the deployment goes wrong. If I can assume it will just destroy everything, or sometimes have to step in and clean after it.
Mm-hmm. So let me try to answer the first one. So if you use the Terraform, which is Enterprise, they already give you a solution for running it. And if you are like a big team, it also comes very useful, and it will make sure that two people don't run Terraform at the same time, for example. But it doesn't do many things around. So if you use that, the credentials part is more or less solved, I would say. But if you don't, then it's a bit of an issue. And essentially, for the last 6 months of the previous year, I was working on figuring that out with my team. And we built a pipeline that sort of pre-provisioned credentials using roles. But we are very AWS based, so I'm not so sure how that translates very well to others, but definitely it's a problem. In terms of, but it's like, at least on AWS, it's very easy to solve. Like we can talk later on if you want. On the second thing, we have had no issues with that, because at least the stuff that we've been running use containers, for example. So in case of an instance going down, like the service would always just sort of come back to it and rebuild it. Some other projects are purely infrastructure, and for those ones, Terraform has some syntax to avoid possible mistakes. And I've said, in my experience, I've never had a problem. So you could put like save things on in your HSL code that says, do not destroy this, never, kind of, or just destroy this before that.
I'm asking, let's say the input was stupid. I just asked for something that cannot be done, but you can't notice until a little bit into the process. What about these cases?
So like, let's say you deleted a server that shouldn't be deleted. But I can't really think of how Terraform cannot go back. Let's say if you had data on that server, I think it's gone. But then, because everything is automated, you can recreate your whole stack in one command, and it probably will take 1 minute to get it all working back to what it was. So from that sense, it always gives me a relief that I could just recreate everything from scratch really quickly.
Thank you. Any further questions? No? Okay, so with that then, I would like to close this talk. Thank you very much. One round of applause, please.